Today we are going to focus on antiderivatives as an areas. Now, integral calculus is mostly concerned with the area below the curve or a graph of a function. So there are many situations where the area can be interpreted in very useful way. So let's look at this case or example. Suppose that a car travels on a straight road at a constant speed of 40 meters, maybe miles per hour for 2 hours, right? For 2 hours. That means for 2 hours. That's t equal to 2 hours. How far has it gone? That's how far has it gone. And that's what the distance. So currently we can get to sketch some sort of graph here to kind of make it easy to analyze. So upon sketching the graph, we can here 0, you can see maybe 0.5, 1, 1.5, and maybe 2.0, and maybe 2.5 going. And we can also number here as well, maybe 10, 20, 30, 40, and so on. Maybe 50 and then 60. So now they said that the car is traveling at a constant speed of 40 miles per hour. So these are 40. We can trace it here. And then continuing the question, they said that it has traveled for 2 hours. So if this is our 2 hours, we can also trace it here. All right, here. So in all, you can see this shape here. So the difference between this and this place is 2. You can see from here 2. That's 2 seconds, right? That's the 2 hours, sorry. It was given in hours, the time. And then from here coming, it's also the speed. All right, that's the y-axis, which is what? 40. The difference, that's 40 minus 0, which is 40. Now let's see something. We all remember that distance is equal to distance is equal to rates of change of velocity over time. So let's see something like this. The velocity this is equal to the velocity times time, right? Distance is equal to the velocity times time. That's what I know we remember. So in this case, the car has gone, d equal to velocity is what? 40 miles per hour times 2 hours, which is going to give us what? 80 miles. Therefore, we can say that, or we can conclude that the car has traveled 80 miles. Then let's look at something here. Based on what we have done here, we can see that we are multiplying 2 times 40. And let's trace something here. You can see this figure is a rectangle. And since the figure is a rectangle, the area of a rectangle is equal to length times what? Breadth. And now our length is 2, and then the breadth is 40, and at the end we are getting 80 miles. But before we make any conclusion, I want us to get to know something small about a second case. So now this is the second case. Now suppose that a car travels so that its speed increases steadily from 0 to 40 miles per hour for 2 hours, the same 2 hours. How far has this car traveled? So let's see or sketch something small here. This is our velocity line, then this is our x-axis, so v, and then this is our t. So the question was saying that the car traveled at a speed increasing steadily from 0 to 40 miles. That means that if here 0, maybe 10, 20, 30, 40, 50, and then we have 1 here, then we have 2 here, and then we have 3 here, and we have 4 here, and so on. You can see that, let me write this one, wow. Yes, here's our t. So we can see that they say it's increasing steadily from 0 to 40 miles. So from here, right, it will go here. And then remember that these are 40. And then they said the car was going at 0 to 40 miles per hour for 2 hours. So we can trace our 2 hours here, right? We can trace our 2 hours here. So now this is the area between the curve and the x-axis. Now we have a triangle. Now that we have a triangle, let's see something from here. When we use distance, or let me start from here, velocity equal to displacement or distance over time, then my distance is equal to v multiplied by t. And now my velocity is 40 minus 0, which is 40 times what? Times the 2, which is still give us 80. And in this case, we can assume that it's correct. So the trouble with our old reliable distance equal to rate times time relation is that it only works if the rate is constant. It only works if the rate is constant. So if the rate is changing, there isn't a good way to use this formula, right? If the rate is changing, there isn't a good way to use this formula. But let's look at this. From this example, we have noticed that this distance equal to velocity times time also describes the area between the velocity graph and then the axis, the t-axis, right? So and therefore the rate is the height of the rectangle, the time is the length of the rectangle, and then the distance is the area of the rectangle. This is the way we can extend our simple formula to handle more complicated velocity questions like this. And this is the way we can answer the second example. So this second example, that's the way that we can answer it. So instead of always rely on this formula, v equal to distance over time, we can say that this distance traveled is the area under the graph. And what is the area under this graph? It's what? Half times base times height for a triangle. If it's a rectangle, it's equal to length times breadth. You can do some for trapezium and other related figures, right? So in this case, we can see that we will have our area as what? 1 over 2 times the base is from here to here, which is what? 2. And then times the velocity is what? 40. And therefore this will cancel this. So at the end we are going to get our area to be what? 40 miles. Right? We are going to get our answer to be what? 40 miles. So let's take note of that. Now let's consider some number of scenarios. And then we relate it to whatever we are coming to do. So the first scenario is a Chelsea cafeteria determines that for the first 50 pancakes produced, its cost is $40 per pancake. What is the total cost to produce 50 pancakes? What is the total cost to produce 50 pancakes? So in this way, we can see that the marginal cost function the marginal cost function, this one of x is equal to 40, right? The marginal cost function of the one pancake is equal to 40. And remember that total cost, the derivative of the total cost give us the marginal cost. Just keep that relation. If it's profits, the total profit, the derivative of the total profits, that's the derivative of the total profit will give us the marginal profits, right? So that's something that I need to take note of. So this is the marginal cost of one, and then the interval is between what? 0 less than what? Let me use t less than or equal to what? 50. So they are asking what is the total cost to produce a 50 pancakes. So based on that, we can mark off the 50 units along the x-axis, right? So if you draw a figure like this, it depends on how you want to trade it. So these are constant costs, right? This, let's say here 40. So you can see our marginal cost going here 40, and then here's 0. So they are asking us how much would that cost if they produce 50, right? So what do we need to do? So at the end of the day is the area under this graph, and the area is what now from here to here is 50 minus 0, and then here is what 40 minus 0. So therefore our length times breadth will give us what? 50 times what? 40. And at the end of the day we are going to get $2,000 or $2,000 for producing 50 pancakes by the cafeteria. So let's move to the second scenario. The second scenario also talking about one of the Ghana's ambulance moving with a velocity is given by the function v of x equal to 3x, where x is in hours and v is in miles per hour. They said we should use geometry to find the area under the graph, which is the distance the ambulance has traveled. So how do we do this? So first of all, let's see something here. We have been given We have been given the function, which is the velocity of the ambulance, which is v of x equal to 3x, where x is in hours and then the v is in miles per hour. So using geometry for this, the graph, we can get a clear overview by sketching some simple graph. So let's sketch some simple graph over here. So this is our t and this is our v. This is our t and this is our v. So let's see something here, right? We can label our x-axis here from 0. Maybe let's start from here. 1, 2, 3, 4, 5, right? And then we can also do same for y-axis, depending on whatever we want to do from here. And now, what we can do is that at we need to plot this graph. So at x-axis, y is equal to 0. So if v of x, it's representing the y. Therefore, at x-axis, y equal to what? 0. And therefore, we can say that our 3x is equal to 0. And therefore, our x is equal to 0. And then at the y-axis, our x is equal to 0. And therefore, we can see that our y, or v, is equal to 3 times 0, which is what? 0. And therefore, our point is 0, 0. So that's where the starting point is coming from when you are plotting it. So it's passing through the origin here. And now the velocity was increasing. So if we put in 1, if our velocity of v equal to 3x, and now our x is equal to 1, we are going to get a value. But the question is asking us during the first 3 hours. So if you want our equivalent v value, the velocity at which it traveled at 3 seconds, what we do? We substitute it inside. So what we are going to get is 3 times 3, which is what? 9. That will be our y value, equivalent y value, or the velocity. So now this is what we are going to have, and this is what we are going to have. We have 9 here. So now we have 9 here, so we can see the figure as a triangle, and then the area of a triangle is equal to what? Half base and then height. Now half, our base here becomes what? 3 minus 0, we get 3, and then our height is what? 9. So from here, what do? 3 times 9 will give us what? 27, and then divide by 2, then we are going to get 13.5 miles. So now, this is the distance the ambulance has traveled at 3 hours. So let's consider the second scenario. So it is said between the 3rd hour and then the 5th hour. So if you look at this place, we can see this is our 5th hour. Here, our 5th hour. So the same, it starts from 0 and it will move here up to this place. But if you want our equivalent velocity value, we want to put in the 5. So 3 times 3x, right? 3x is equal to 3 times what? 5. And therefore, let me use dot so that I don't confuse with the x. 3 times 5 equal to what? 15. So now, 3 times 5 is our equivalent velocity for the second one, right? And then the same thing, they say is between the 3rd hour and then this one. And then when we look at this one as well, we are also going to get 3 times v. The second one is 3 times 3, which is what? 9, right? So you can see that here we have a rectangle inside and we have a triangle inside, considering this top. So here is the triangle and here is the rectangle. So for the rectangle, you can calculate it straight away from it, which is what? 5 minus 3. 5 minus 3 times, and from here to here it's what? 9. So 5 minus 3 is 2 times 9 is what? 18. And now let's look at the triangle. So the triangle part, when we substitute this one, the whole of this length here, we are going to get 15. And we substitute the whole of this length here, we are also going to have 9. And this is the height that we want from here to this place. Therefore, we are going to get 15 minus 9. Or let me write it here, 15 minus 9. And now we are going to get what? 6. And therefore, area of a triangle is equal to half base times what? Height. So half, the base is what? 2, because 5 minus 3. And then the height is what? 6. So now this will cancel, then we're going to get what? 6 miles. And in total, the area of the triangle, right, plus the area of the rectangle, right, will give us what? 6 plus 18, which is what? 24. So in all, the car traveled, or the ambulance traveled at a distance of what? 24 miles between the 3rd hour and then the 5th hour. So this is the interpretation of whatever we have gotten. We have a lot more 2 scenarios to go, but because of time, I'll leave the other 2 for you so that you can do here. Mr. Joshua's tech point named the marginal profit and the marginal profit function, which is modeled by the linear function P prime x equal to 0.15x, where x is in months and P prime is in thousands of dollars per month. Sketch the graph and use it to determine the total profit earned by Joshua's tech point in a year. So this is a solution. You have a solution here. So basically, what I want to do is that I'm not going to do this question, but what I'm going to do is that I'm going to give you a clear overview so that you can know what to do. So this is your marginal profit function. As we did for this one, follow the same procedure. That's it. Just plot your function. Just plot it on a graph. At x equal to 0, y is 0, and then at y equal to 0, x is 0. So from 0 to that means it will start from the origin. So if it's starting from the origin and they are asking us in the thousands of dollars per month, sketch the graph and do this. So in thousands of dollars per month in a year. So how many years in the months is in the year? So that's 12. That means your end one is going to be 12. And then at the end of the day, you are going to get something like this. You are going to get something like this. And what you need to do is just use, if you want to convert to hours, you can use, or you want to convert them into years, you can use years. If you want to use it in months, you can use month, and then find the area, half, base, times height. That's all about the Joshua's tech point. And then I think that's a last one that I wanted us to talk about. Yeah. So now let's consider something here. So how do we approximate the area if the rate is a curve? How do we approximate the area if the rate is a curve, but not the normal figures that we see here? If the rate is a curve, how do we compute this area? So in this case, the area function is an antiderivative of the function that generated the graph. And therefore, how do we handle such curved graphs for which this area formula may not be known? And this is where the Riemann summation comes in. So keep watching, and my next tutorial will be about Riemann summation, and we are going to delve deeper into how we can use Riemann sum to approximate the area of a function. And if time permits us, I'll also try and use GeoGebra to do Riemann sum so that you can also get yourself involved in a bit of technology to know how you can use technology to do integration. Thank you, and see you in my next video.